So that particular Frobenius symbol, remember that we have obliterated the main diagonal of the partition, so the entries in the Frobenius symbol do not add up to the number in question. So the first thing we do is to add 1 to each of the entries of the bottom row, so that now all of the entries there will produce the number in question. And now we use the Frobenius symbol as a code for the walk. Namely, the 2 means that there are 2 steps up the y-axis, then the 3 goes to the right, then this 3 goes down, then you go, and so you follow the green arrows, and at each stage you put this number of segments in, and this is the correspondence between these partitions and these CSSAWs. I would also point out that one thing that is not illustrated by this example is the fact that if there is a positive number at the end of the top row, you're going to have an even number of turns in the you're going to have an odd number of turns in the walk. If you have a 0, so you're going to have an even number of segments, I should say. If you have a 0 here, then you don't start with this 0, you start down in this corner, and that would give you the walks with an odd number of horizontal and vertical segments. Okay, I want to go back now to the picture that we had here with this picture, and to note something about these things. Namely, 3 of these have an even number of turns, and 4 have an odd number of turns. So it's the first and the second, third, fourth, and fifth have an odd number of turns, namely 1. The first one has no terms, and the last 2 have 2 terms. Now I want to turn, so we've just seen that these walks, these CSSAWs, are in one-to-one correspondence with partitions. And so let me now note what the partitions of 5 are. And what I want to point out, so I learned a new term yesterday that had somehow escaped me, namely the MEX of a set is the minimal excluded element, and that's precisely what I'm going to look at here. Namely, I'm going to look at the smallest number that is not, the smallest positive integer, that is not a part of the partition. And so you see that in these partitions, 3 have a smallest missing even, and 4 have a smallest missing odd. And as you just saw on the previous screen, 3 had an even number of turns, and 4 had an odd number of turns. And this is not just a fluke for 5, but it is true in general. So I want is to show you precisely why that is true, and then to lead on to other questions that are related to the other topics in the title of my talk. So I hardly need to put this slide up, but I will anyway. This is the standard notation for the Q series, basic hypergeometric series. And so the question is, if you think about the previous case, in order to get an even number of turns, one either looks at, so to get an even number of segments, you have a positive integer in the last row, and to get an odd number of segments or an even number of turns, you have 0 in the top row. So we're going to look at those generating functions whose Frobenius symbol has no 0 in the top row, so that it has positive entry, so we're going to have an odd number of turns in the related CSSAW. So what is this? Well, this is just standard partition theoretic argument. You sum up then noticing that you have generating functions for partitions into distinct positive parts with the A's, distinct non-negative parts with the B's, and so you get these two finite standard generating functions. You put all this together, and you have a series that looks very much like one of the classical formulas for the partition function, but it's just not quite right because of that plus n there. And in fact, it is possible to prove by standard means that that series is actually equal to, now here we have the false theta function divided by the standard Euler infinite product. And you can rewrite the false theta function as I have done here, collecting together each even and odd term so that the minus signs are collected there. And now you can rewrite this expression as this, and you see precisely what's happening in this last series, namely each term has the first missing partition in the partitions being generated. The first missing part is this number 2n plus 1. And so this gives us this one-to-one correspondence between partitions with smallest missing part odd and the Frobenius symbols with a positive entrant in the top row, and therefore an odd number of turns in the CSSAW. So that's my indication of, so to speak, the direction of this talk, but I wanted to start with that example to show you that the classical false theta function, one of the ones that Ramanujan studied most, and that interested L.J.Rogers as well, was indeed applicable in a wide combinatorial setting. So let me review a bit of history and go more to the Mach theta functions, because my most recent combinatorial study of partitions led me to the developments that I want to highlight in terms of how further applications of false theta functions. So basically, my original interest stemmed from one of the false theta functions, which in that last letter that was my first slide, going on from that particular page, were a list of many Mach theta functions, and the series you see in blue here is one of them. And so what I am proposing is to look at sequences that would allow you to put this into something like the standard transformation that was done by W.N. Bailey. I probably should just put it on the screen here rather than on the, so I hope people can see this, but basically you have a summation beta n q to the n squared equal a summation alpha n q to the n squared divided by this q infinity. And this I will be referring to often. And so in that particular series in blue, what you want is the beta n that you see there in red. If you can find out what the alpha n is, then you might be able to say something important about the Mach theta function. Well, so here are what it is possible to determine what the alphas are by a standard algorithm. And if Ramanujan himself had been doing it by hand, these are the alphas that he would have found. And they are not terribly illuminating. But as Doron will appreciate, we live in the age of computer algebra, so we don't need to stop at 3. We can go on up, for example. And by this time, it becomes quite clear that something is happening that is